Greetings, Astronomy 10, and welcome back to your Chapter 16 lecture. Today we're going to be talking about cosmology, or the beginning of the universe, and the Big Bang Theory. And we're going to be going into some depth about the evidence for the Big Bang Theory. Basically, in essence, all scientific theory kind of points towards the Big Bang. So this is basically another case of we call things theories because all of the evidence that we have supports it. And just because it's a theory doesn't mean it's wrong. Very much like, I gotta clean off the lens here real quick. Just like the theory of evolution is a theory because all of our scientific evidence points towards it, right? It's a necessary and logical conclusion. Okay, so if we think back to Hubble's law is the idea that, the further away objects are from us, distant galaxies and so on, the greater their redshift, or the greater their velocity moving away from us is. And so that means, essentially, that the universe has to be expanding, if you remember. Now, if the universe is expanding, and the universe at large, everything in the universe is expanding, right? Things that are far away from us are moving away from us even faster because the entire universe is expanding. That also means, obviously, if we run the clock forward, things are going to be further apart, but if we run the clock backward, that also means that things had to be closer together at some point in the past, right? Stands to reason. And if we run the clock backward, we realize that about 13.7 billion years ago, the universe must have come from one single place, one singularity in space and time. We call this 13.7 billion years Hubble time. And we take that from the inverse of the Hubble constant, right? And the respective distances that things are from each other now. And we call this event, this beginning of the universe where everything just kind of came from, we call that the Big Bang. Now there's a link to a video that's narrated by Stephen Hawking that's a computer simulation of the Big Bang event and what was supposed to have happened around that time. It's pretty good. I would recommend that you go ahead and have a look. So this is a good time to pause the video and click on that link. Okay, as we saw from the video, most galaxies in the universe are essentially hurtling away from each other. There are notable exceptions, of course, like our own local group, where all of the the galaxies like us, the Milky Way, and the Andromeda Galaxy, Triangulum, we're all gravitationally bound to each other and we're eventually going to collide, right? Even now, we're cannibalizing galaxies like the Magellanic Clouds and the Sagittarius Dwarf Galaxy, right? The universe at large, however, if we want to talk about larger scales, right, galaxy clusters, not just local groups, right? We're talking about galaxy clusters and superclusters and the distances in between superclusters and things like that. These galaxies and galaxy clusters are hurtling away from each other through space and time. If we look at two galaxies that are kind of far away from us, we know how fast they're moving away from us, right? Because we can measure their redshifts, right? How quickly they're Doppler shifted away from us, and therefore their radial velocity, how fast they're moving away from us. But also, because we can see the direction that they're moving, right, we can tell how fast they're moving away from each other as well. And if we know how far away they are from us, and therefore each other, we can kind of run the clock backward to figure out when the Big Bang was supposed to have happened. That's our Hubble time. Now, there have been a bunch of I don't want to use any nasty adjectives, but some interesting standpoints, let us just say. Naysayers may try to convince you that if space-time has a certain what we call curvature, then our estimate for the age of the universe may be different than this 13.7 billion years. If space-time has negative curvature, then essentially the universe should just expand forever. And if the universe has positive curvature, then the universe should eventually kind of fall back onto itself. And some people have speculated that that may cause another Big Bang, and who knows, right? However, all evidence points to the universe and space-time having zero curvature. Nothing, right? Everything is kind of flat. You look in a straight line to the edge of the universe, and some light just happens to come straight at you without any gravitational lensing or whatever, then it actually came in a straight line, right? There was no funny curvature in space-time. Lots of textbooks will try to tell you that the universe is infinite, and therefore we cannot estimate the age of the Big Bang. However, this is a theory that has long since fallen into disfavor among scientists, for the simple reason that things that are infinite don't have beginnings. I'll let that one sink in for just a second. When I think about people talking about an infinite universe, I always get reminded of that scene in Raiders of the Lost Ark. You know which one I'm talking about. If you haven't seen Raiders of the Lost Ark, it's maybe one of the best Hollywood movies that was ever made. There's a scene at the beginning of the movie where Marcus Brody, who is one of Indiana Jones's best friends and colleagues at this university that Indiana Jones teaches at, he's trying to get Indy to go and look for the lost Ark of the Covenant. And we're not going to get into, all the religious implications or whatever, because, well, for one, it's a spoiler, and I don't like messing up movies for anybody. That's not cool. But suffice to say, he's trying to go and convince him to go and look for the Ark. And, as Indy is making preparations, they're having this verbal exchange. Marcus Brody says to Indy, "Marion's the least of your worries right now, believe me, Indy. Well, I mean, for nearly 3,000 years, man has been searching for the lost Ark. That's not something to be taken lightly. No one knows its secrets. It's like nothing you've ever gone after before." And Indy says, "Oh, Marcus, what are you trying to do, scare me? You sound like my mother. We've known each other a long time. I don't believe in magic, a lot of superstitious hocus pocus. I'm going after a find of incredible historical significance. You're talking about the boogeyman. Besides, you know what a cautious fellow I am." Obviously, in this case, the boogeyman is this supposed infinite universe that a bunch of scientific naysayers will try to tell you is what the universe is actually like. We know that the universe is probably larger than the observable universe, larger than what we can see, but we don't know. But what we don't know is exactly how much is beyond our limits, right? We know that light has only traveled about 13.7 billion light years since time began, and so we can't see any farther than that. However, our model for physics, our theoretical model, predicts that at a very short time after the Big Bang, the universe underwent an unprecedented period of expansion. We call that inflation. And so the universe is thought to be much larger than this 13.7 billion year radius bubble, right? It's probably at least 100 billion light years in diameter, so much, much larger. And this, of course, is due to the fact that space-time itself is expanding. In any case, the evidence for the Big Bang Theory is everywhere, quite literally everywhere in the universe. There is a 3 Kelvin energy signature that's kind of everywhere, and that's residual energy left over from the Big Bang, from the event itself. To put that in proper context, 3 Kelvin is 3 degrees C above absolute zero. So you're talking about minus 270 degrees C. Very, very cold, very low energy, but non-zero, measurable, right? And that was kind of discovered on accident by two scientists named Wilson and Penzias. And they were accredited with the discovery of this phenomenon we call the cosmic microwave background radiation. These two were working on a project called the Holm-del-Horn antenna at Bell Labs. And they were trying to do some basically radio astronomy so that they could communicate with satellites out in space. And although other groups, there was like a group from Berkeley that had predicted that this was out there, Wilson and Penzias used this Holm-del-Horn antenna to find it. And legend goes that they were trying to find like an empty patch of space so they could calibrate this antenna to zero, to no input energy. But no matter where they pointed it in the sky, they found this very faint, very weak, very cold, very low energy source everywhere they looked, no matter where they pointed it in the sky. And the legend goes that because they couldn't shake this energy signature, they thought that, they needed to clean it out, and that like a bunch of pigeons had made a mess in it. So they went and they cleaned it out. They cleaned it out as perfectly as they could. They made it all nice and shiny, right? And after cleaning it out and making it perfectly clean, like totally sanitary, totally and completely sterile, they realized that the energy signature was still there. And it wasn't until later that they had realized what it was they had actually discovered. But what was it exactly that they had discovered? They had come up with this really, really cold microwave radio signal, essentially, right? So sometime after the Big Bang, the universe was in a much smaller volume than it is now, right? It's this, 100 billion light-year diameter sphere, probably, volume that has tons of galaxies and dark matter and all kinds of stuff in it, right? And so if it's really big now, at some earlier time it must have been much smaller, right? So in the early universe, the universe was still very, very hot and very dense. And at a short time after the Big Bang, the universe was so hot and dense that essentially all of the matter was loose protons and electrons. It was so hot that, the volume of the universe was so small that all of that energy made all of the individual particles so hot that they were just kind of moving around really fast and banging into each other, so much so that it was impossible for protons and electrons to combine and make stable hydrogen atoms. It was too hot. They would kind of instantly ionize if they wanted to try to get together. If one of those electrons was going to try to enter the ground state orbital around one of these protons to make a stable hydrogen atom. And it wasn't until probably about almost 400,000 years, something like 378,000 years after the Big Bang, that what we call the recombination event occurred. And protons and electrons were allowed, essentially, to combine to make stable hydrogen atoms. So this recombination event occurred, and when that happened, when the universe, expanded enough that the energy density dropped below the necessary threshold for protons and electrons to combine to make stable atoms, shortly after that, the electromagnetic radiation, the photons, the light energy of the universe, became decoupled from the electrons and protons, right? They weren't getting bounced around in between particles and reheating and getting released and all that. And so After that point, after recombination, photodecoupling allowed light to permeate the universe. And from that point onward, the cosmic microwave background radiation began to travel throughout space and time. So if we looked at the amount of energy that was supposed to have been released by the Big Bang and the energy density in the universe that was about this certain size when this recombination and then photodecoupling happened, we should be able to figure out exactly how hot the energy density that was released into the universe, this cosmic microwave background radiation, was supposed to be. So essentially, the heat left over from the Big Bang should have left a black body radiation curve, right? Because you're talking about a hot universe, right? So our theoretical predictions of how hot the cosmic microwave background radiation should be, according to how much energy and volume there is in the universe now, predicts a black body curve with a peak of heat radiation about 3 Kelvin. And this puts the Wien's displacement law electromagnetic radiation peak somewhere in the microwave radio region of the electromagnetic spectrum. Hence, cosmic microwave background radiation. Now it sounds interesting and maybe even a little crazy, right? And a lot of this is based on very sound but also very theoretical physics, unless you spent tons of time studying it like people like me did. It all sounds maybe a little bit foreign, right? But suffice to say that yes, this did happen. There was a Big Bang. There was a recombination event, and so like this fog was kind of lifted from the universe, and then light got to pass through after recombination, right, and photodecoupling. And in order to show that we were right, we sent out a probe into space that we called COBE, C-O-B-E, C-O for cosmic, B for background, and E for explorer, in order to try to take precise measurements of the cosmic microwave background radiation without any atmospheric interference. And what we found was there was a peak at about 2.75 Kelvin, right about where we thought it was supposed to be, right? So our first measurements of the cosmic microwave background radiation were not super great. And it wasn't until we sent out COBE, and then we sent out another probe. I forget the name. I'm just going to look it up. It's the WMAP, right? The Wilkinson Microwave Anisotropy Probe. The WMAP. That one actually gave us even better, even more accurate depictions of the black body curve left behind by the cosmic microwave background radiation than COBE did. COBE went into space in 1989, and WMAP was in 2003. So that was even more recent. In any case, our first measurements of the cosmic microwave background radiation were not super great. And if you look at today's image bank, if you look at, I think it's the 14th image, it just kind of looks like a blue and red yin and yang, right? The black and white things that kind of rotate around each other. But that's kind of what our first measurements looked like. They weren't great. And we had to try to realize what exactly it was that we were doing wrong in order to try to make sense of it. And if you look at the image immediately thereafter, we kind of realized that all of the material on one side was red shifted and all the material on the other side was blue shifted. meaning that we weren't accounting for the Earth's rotation. But after that, it got much better, and then eventually, the next picture after that, I think, is Kobe, and the one after that is the W map. And we can see that the measurements are getting better and more refined, and now that we've actually so the first one after subtracting for the Earth's rotation was still under the Earth's atmosphere, and then when we actually sent probes out into space, the measurements of course got much better, right? The cosmic microwave background radiation apparently is not even in all places. There are cold spots, or places where the energy density of this cosmic microwave background radiation is less dense in some regions than others. And it is thought that it's possibly due to a greater density of energy becoming matter via the Higgs field. If you remember, we talked a little bit about the Higgs boson, the quantum field by which matter achieves mass, right? In any case, matter has become energy, or energy has become matter as a result of the Big Bang, right? So our model seems to predict that the amount of matter in the universe should sort of determine the ultimate fate of the universe. And the going theory was that if there's enough matter, it should cause the universe to collapse back onto itself and into a singularity again. And if there's not enough matter, the universe should expand forever. And if there's exactly the right amount of matter, after an infinite amount of time, the universe should just stop expanding. However, Einstein predicted that none of these was correct, and he was right. But the way that he figured it out, which was kind of accidental, because he called this thing the cosmological constant, it wasn't like the way that he originally intended it to be. And so he called his discovery of the ultimate fate of the universe and some of the greatest possible theoretical physics questions, he called the answer that he came up with, which was correct, accidental or not, he called it the greatest blunder of his career because he was not able to anticipate it properly. So if we think back to when Einstein was around and still practicing physics, that was around the turn of the 20th century. And at that time, remember in the 1920s, Shapley and whatever the other guy's name was, Harlow or something, they had this great debate because nobody could wrap their heads around the idea that the universe was larger than the Milky Way galaxy. So Einstein wrote an equation that was supposed to balance gravity with the expansion of the universe, right? And so the universe was kind of supposed to stay static in the Milky Way. And so when he wrote his equation that was supposed to balance gravity against the expansion of the universe, he wrote a little fudge factor in it called the cosmological constant in order to try to keep the galaxy, which at the time was accepted to be the universe at large, static and approximately the same size. When it was found that the universe was expanding, the scientific community had already forgotten about the cosmological constant. However, when we discovered that objects near the edge of the observable universe had greater redshifts than predicted, Einstein realized immediately that his cosmological constant was not zero, that it was there, that it was real. And he said that his inability to predict this was the greatest mistake that he ever made. However, he, just like all of the other scientists of the day, had absolutely no idea what the cosmological constant was. But it seemed that there was some kind of force that was causing the universe to expand, and this is acting opposite to gravity, which is, of course, an attractive force and would cause the universe to contract, if anything, right? But what was it? What was this thing exactly? Well, there are four fundamental forces in nature, right? There's gravity, there's the weak and strong nuclear force, and there's the force of electrostatic attraction. And whatever is causing the expansion of the universe is not one of these. Judging by the fact that the effect is more noticeable for objects that are farther away, space-time itself has to be expanding. Now, there's really no reason for that to happen that we are 110% sure about as of yet. There are some theories that predict that these things might happen, like supersymmetry, and I think there's a consequence somewhere in what we used to call string theory, what we call M theory now, that predicts that maybe something like this should happen, but neither of those have been proven. So basically, we are not really sure why it is that the universe is expanding the way that it is. And as a matter of fact, the universe is expanding about 63% faster than we have any reason in theoretical physics to predict that it should continue to expand. And we call this missing 63% of mass and energy, whatever it is out there in the universe that's causing the universe to expand. We call this expansion, or the impetus for this expansion, dark energy. And we call the fact that we don't know where this energy is coming from or what it is, we call that the dark energy problem. Now, it may be possible that there's an explanation, in this thing that we call the Dirac sea, which is the idea that essentially there is an infinite number of this possible energy for pair production and pair annihilation, which is happening everywhere all the time, right? The quantum foam. And therefore also Hawking radiation. There also may be an answer in the structure of matter itself, but again, our understanding of that is complete. But that doesn't mean that we won't figure it out, right? We did manage to figure out the Higgs mechanism. The Higgs boson, of course, is the particle associated with the Higgs field that is the Higgs field, of course, is everywhere in the universe, right? Not just at the Large Hadron Collider at CERN, where we found the Higgs boson, but essentially, as energy travels through the Higgs field, quantum excitation causes Higgs bosons to slow down the energy and take on mass, right? Essentially become matter, sort of. And so we detected the Higgs boson on July 4th, 2012, so maybe we're not actually that far off. There's also some thought that this thing that we call M theory, what we used to call string and then superstring theory, may hold the answer. And that's kind of a nice sentiment. String theory is really interesting because the basic premise is that energy kind of makes up everything. And if energy oscillates at like a certain quantum state, if you want to think of it that way, it makes like an electron or a quark or a proton, or technically a bunch of quarks make up an electron and a bunch of quarks make up a proton and so on. But in any case, we don't have a lot of evidence for M theory or string theory, and we don't have any evidence really for supersymmetry either, although those may hold the answers. But M theory might be able to explain the otherwise seemingly inexplicable, not easily explainable, right? Impossible to explain the behavior of the electron, the inexplicable behavior of the electron. But that's all speculation. None of us know for sure. In any case, I hope you've enjoyed today's lecture as much as I've enjoyed giving it. If you have any questions, please get a hold of me through the normal channels, and we'll see you next time.